Thank you, Mr. Chairman, and thanks to the organizers for inviting me to this conference. So my talk is entitled A Wireless Sensor Network Infrastructure for Personal Monitoring. So this is the outline of the presentation. I will start with a short introduction on wireless sensor networks and on the standard IEEE 802.15.4 and ZigBee for wireless sensor networks. Then I will go with the main part of the presentation, which will be the wireless sensor infrastructure we have developed. I will also explain some personal health applications based on this infrastructure, and I will end with some conclusions and future work. So, in general, a wireless sensor network is a group of distributed autonomous devices which may include some sensors, either physical or environmental, and which communicate through wireless technologies. The two main topologies of wireless networks are the ones you can show in the picture. The star topology, where you have some endpoints connected, all of them, to a central gateway, and the mesh topology, where each node of the network is operating as a router, and all the information is gathered by a central gateway also. So in the picture on the right, you can see the OSI levels of ZigBee plus 15.4. So the 15.4 standard is covering the low layers, the physical and medium access layers, and ZigBee is dealing with the network and application layers. On the table on the left, you can see the most typical requirements of wireless sensor networks, and on the right column, you can see how ZigBee and 15.4 answer these requirements. For example, low data rate is provided by two physical layers, one with 20 or 40 kilobits per second, and another one with 250 kilobits. The robustness required by the networks is provided by the physical layer with some spread spectrum techniques. Regarding energy efficiency, the medium access layer is optimized for low duty cycle applications. For scalability, the network layer is providing a hybrid three-mesh topology. And for self-configuration, the application layer is giving device banding and service discovery mechanisms. So overall, we can conclude that the combination of 15.4 and ZigBee is a suitable communication technology for sensor networks. So the wireless infrastructure developed here is made of three main components: a fixed wireless sensor network, a mobile personal device, and a mobile sensor node. The fixed network is made of fixed nodes with contain optional ambient sensors. And the data, they route all the data from all the devices to the central gateway, as you can see in this picture here. The mobile personal device is made to be connected to a PDA or to a mobile phone through an SD adapter. And it can be connected to the fixed network or also to the mobile sensor nodes, creating a body area network, as you can see below here. The mobile sensor node contains normally a body sensor, and it can also be connected to the fixed network or to the mobile personal device. This node has some critical features, which I will go into more detail later. The first element, the fixed network, is normally implemented in buildings as a mesh network, and it's based on a system-on-chip, a commercial system-on-chip by Texas Instruments, which has two parts: as a 15.4 plus ZigBee transceiver, a 15.4 transceiver on one side, and also a 8051 microcontroller with the set stack, which is the ZigBee stack by Texas Instruments. All these nodes are connected to the mains power supply, and as I said before, some ambient sensors could be included. For the case of including high sampling rate sensors, the 250 kilobit per second could be a limitation for this system. So a power line extension is foreseen where some of the routers in the network operate as bridges from ZigBee to power line. The function of the mobile personal device, the second element, is to monitor body parameters when the user is out of the fixed network, as could be the case in this picture. So it means that it's acting as the coordinator of a body area network with the rest of the mobile sensor nodes. As you can see in the picture, it's possible to include this board on an SD card adapter to insert it on a PDA or mobile phone. and it's based on the same system on chip as before. For mobile sensor nodes, they contain body sensors, either to monitor physiological parameters, and they can also store some user data for user identification, allergic problems, or medicines. It's based on the same chip, and as I said before, there are some critical features such as size, power consumption, antenna body interaction, and mobility. I will go into more detail into the three highlighted aspects. Regarding power consumption, in this kind of wireless sensor networks, it's normal that the nodes stay most of the time in a sleep mode where the power consumption is very low, normally less than 1 microampere. However, when they transmit or receive, consumption could go up to 28 milliamperes, as in this case. In this plot, you can see the evolution of the consumption on the chip when it starts waking up. So it goes through several power-up stages, and finally it transmits a frame here, and it receives an acknowledgement, and then it goes back to sleep again. For this kind of nodes, lithium manganese dioxide batteries are used normally. The two most popular formats are the CR2032 and the CR2432, depending on the capacity required. The current peaks, it should be noted that current peaks can create some depolarization on the battery and also the reduction of the capacity. We have measured some lifetime reduction between 20 and 50%, depending on the cycling, on the number of cycles. Regarding the antenna body interaction, normally in this kind of body applications, the body is in the near field of the antenna. On the other hand, if we are at RF frequencies, let's say gigahertz range, the penetration depth of the waves in the tissue is around 100 millimeters. This means that communication through